So, hello everyone, my name is Dripto Debroy. I'm a fourth year grad student in Ken Brown's group at Duke University, and I'll be talking about a technique we developed called stabilizer slicing, which allows essentially to have some resistance to coherent error noise in our stabilizer measurements. So this is work done with Muyan Lee, Michael Newman, and Ken Brown, and essentially it's a technique that exists somewhere in the layer between quantum error correction and gate compilation, and it uses the symmetry of stabilizer states in order to sort of direct gate errors opposite each other and have them cancel out without us having to know too much about the strength of our noise. So with that, let's go into overview of sort of like what coherent error work has been done in QEC already. So generally we expect them to be worse than stochastic errors. And the reason for that is that they increase quadratically. So when you combine n stochastic errors, you end up with a stochastic error that is n times the probability. However, coherent errors are unitary and look like rotations. So when you combine n of them together, you get a rotation with n times the angle. And because the probability is or sine squared of theta, you'll end up with a quadratic increase as you build up these coherent errors. So general intuition has been that that's bad. You don't want your errors to be increasing rapidly. And so these errors are going to be harder for us to correct. Most research so far has been a memory error. So this is some sort of like small IID rotation that's constantly occurring in your system. And there have been a few techniques. So there have been three sort of like major research thrusts about coherent error, sort of in painting broad strokes. So ways to get around them, so dynamical decoupling, which has been talked about a few times in this conference already. Random compiling, which basically has the goal of having your coherent errors not be in the same direction so they don't add. And these sort of help at high coherence, but do add some overhead. And because of that overhead, if you had a complete uncoherent system, you're adding just extra gates to your system. And you could see a mild loss. A lot of work has been done, this is only a small subset of it, on quantifying how bad these errors are. And they generally find that these are worse than stochastic errors, but not sort of horribly worse. And generally they're just like, it's a slight like, small factor increase. And then there's been work on how these errors interact with distance, and they generally find that as distance increases of your code, you end up seeing that your coherent errors become more stochastic in nature, or like look more stochastic. And there's also a poster by Joe Iverson in the poster session that talks about coherent error as well. So if this is interesting to you, check his poster out as well. So with that, let's look at our particular problem. So in many computer architectures right now, gate error is a major concern. And we want to basically avoid the situation where you have a clean code state coming in, you measure your stabilizers in order to check whether or not you're in a clean code state, and you actually damage your code in the process. So we're trying to look at sort of basically gate error and how to remove gate error from our system. Depending on the architecture, this error comes from coherent over rotation, which is what we'll be talking about. And so that's a unitary channel in the direction of the gate. And our basic goal is to use this sort of structure of like knowing the direction of the errors and stuff like that in order to have them coherently cancel out. And as a physical motivation for these sort of over rotation errors, we can use sort of a current architecture example. So in ion traps, a miscalibration in laser intensity or in terms of timing can lead to a coherent over rotation. So if your laser is slightly too strong, every gate you apply with that laser will have a slight over application of that gate. Similarly, in almost any architecture, if your timing is incorrect, if your clock cycles are badly calibrated, then you're going to over under apply your gate every time you apply a pulse. And then even for architectures that have issues with T2 time, our technique does help with these gate errors. However, obviously we can't do anything with T2 time. That has to be dealt with separately. So what is a coherent over rotation? So in quantum error correction, these are more damaging, I mentioned. They have non-zero off-diagonal terms in the process matrix, along with the quadratic addition of the error probabilities, as I mentioned earlier. And but they are invertible. So that's sort of our upshot, is that they build up badly, but if we can find these inverses and apply them, we can theoretically apply, like, cancel out our error without having to look at our stabilizer values and syndromes, et cetera. And then here what we have is a ion trap decomposition of a control knot. This talk will be in terms of ion trap stuff, but all of this applies to any architecture which has a 2-qubit poly rotation as the sort of basic entangling operation. And then so if in ion traps you break down gates into single qubit poly rotations along with this 2-qubit XX type Molmor-Sorensen gate that we've heard a few talks about so far already. And then in red I've put in the over rotations that occur from a 1 plus epsilon sort of intensity excess on your laser. So if your laser is epsilon% too strong, then you will have a 1 plus epsilon factor on all of your single qubit gates and a 1 plus epsilon squared on your 2 qubit gates. And then here, these S and V parameters are arbitrary plus or minus 1s, and any of the 4 choices of S and V plus minus 1 gives you a valid control knot up to global phase. So this is all first talked about by Dmitry Maslov, and when this was initially thought of, these were used mainly to cancel out single qubit gates. So if you have a bunch of control knots in your circuit, you can pick S and V for each control knot such that you minimize single qubit gate count, and that will be part of what we do as well. However, we really care about this S parameter right here. So basically, by changing S and any of these parameters, we're changing the direction in which our coherent over-rotations are occurring without having to actually know what they are. So I'm going to say over-rotation this whole time, and under-rotation is just a negative sign on epsilon. It works the exact same way. And the idea is that without knowing whether we're under-rotating or over-rotating or whatever, we can direct our gate errors and make sure that we have some sort of control over the direction of these errors. And then the last thing I want to mention is, so these S parameters are important. The V parameters tend to be how you cancel single qubit gates out. And we'll talk about that in a little bit. So just to go over our error model, after every gate, after a gate G, we apply this channel right here. So there's 2 major parameters to this channel. There's this kappa parameter, which we call the unitarity. It's a different unitarity definition than the one here. It's a bit simpler and just sort of a linear mixing between coherent and stochastic. And then so at kappa equals to 0, you're in a stochastic channel, so that's this epsilon s. And that's essentially a twirled approximation of what an over-rotation error would be. And then at kappa equals 1, you're in the purely coherent channel, which is right here. And that is a small rotation about the g-axis. So g could be a X gate, it could be a Molnar-Sorensen gate, etc. And then basically the thing that's nice about these 2 channels is that they're picked such that their fidelities are equal. So as you modulate kappa, your fidelity of your error channel does not change. So basically in the following plots I show you, I'll be modulating kappa, but the error channel we're applying will be the exact same strength the whole way through. So kappa is independent of your fidelity. Your fidelity is just dependent on this epsilon parameter. And you have basically 2 knobs to turn on this error model. Okay, and then this, just want to mention this stochastic channel here has been studied by Colin Trout et al. In a paper that came out last year. So to apply our method, we'll need 2 conditions. Both of these do have workarounds I'll talk about later to varying levels of effectiveness. But the first one is the freedom to apply any rotational gate in the clockwise or counterclockwise direction. So this is basically the control of that S parameter in my last slide. And this is essentially how we're going to direct our errors. Important thing to see is that if I ask for example, a minus pi over 2 rotation, if your architecture automatically puts in a plus 3 pi over 2 rotation, while the gate you're applying is the exact same, these over-rotations will look different. So they'll be directed in opposite directions, and the 3 pi over 2 version will have 3 times the strength. So we do rely on having control over this parameter. You can't just sort of look for complementary angles. And then the second thing is for a 2 n-body stabilizer, you'll need n plus 1 body Hamiltonians. So this is why we're kind of motivated to keep stabilizers relatively small. And that's because we really rely on that to control the exact structure our errors look like. So if we can control what gates G we're applying, then we can control what errors are appearing in our system. So this first condition is satisfied in many, if not all, architectures at the moment. In ion trap, computer corresponds to that S parameter, which is the direction of your Molnar-Sorensen gate, and that corresponds in our physical system to Raman beam phases. But similar ideas happen in all other architectures. Okay, so with that, we're going to start getting to the basics of the system, or the technique. So first, we take some stabilizer S. On the left here, we have sort of the standard stabilizer measurement circuit. So you have some qubit, and still qubit in the plus state. You apply a controlled S operation to your code state, and then you're going to measure this qubit in the plus-minus basis to find out whether your stabilizer is violated or not. So our first thing to do is to slice this stabilizer into 2 pieces, SL and SR. So in this way, we're really controlling what over-rotation errors are appearing. So all of our errors are going to appear as a controlled SL or a controlled SR type over-rotation, or some analog of that. So then what we do is we apply these 2 rotations as pi rotations about some arbitrary axis, where the angles are chosen so the gates rotate in opposite directions. So what we're doing there is we're basically choosing how to direct our errors. And then, so here we've done counterclockwise, clockwise, but both are valid. And then, due to this, our over-rotations will cancel out on our system. So let's sort of look at that a bit more formally. We have some stabilizer S. When applied to psi, gives us psi back. So that's basically just us saying your stabilizer is not violated on this particular code state. So we break S up into two pieces. Here they're disjoint, so they're going to both be Hermitian Pauli operators. They're going to square to 1. So S is equal to SL times SR. You multiply by SL on both sides. It'll go to identity on this side, and then you'll end up with SR is equal to SL when applied to psi. So this is really the symmetry we're using. The errors on SL, or an error of the type SL, looks the exact same as an error of the type SR when applied to a valid code state. So then as a result, any small rotation about SR will look like a small rotation about SL. So then here what I have is the gate errors that occur after a controlled like CSL and a CSR operation applied to your state. So we have a small angle epsilon theta L rotation about the CSL direction, and then a theta epsilon theta R CSR rotation as well. So when we use our two sort of facts we've put in, we first take theta L to be pi and theta R to be minus pi. So again, minus pi and pi is also a valid choice. And then we apply SR with SL. So now we have e to the I epsilon pi CSL and then minus e to the I epsilon pi CSL. These are unitary inverses and they cancel out. So we've put the gate error from our error model onto our system, and then, this in the purely coherent case at least, and then we see that because of the structure of how we have applied this circuit is now resistant to that over-rotation noise. So that's, in essence, the technique. One thing to note here is that you need to slice S into two pieces natively. If you slice it into 3 or 4, for example, and let's say you have S1, S2, S3, then S1 is going to look like, when you take this conjugate sort of identity, S1 is going to look like S2 times S3. And so you won't be able to cancel that out by over-rotations of S2 and S3 individually. That would be the same thing as saying that you can take two single-qubit Pauli rotations and create a 2-qubit native Pauli rotation, which we all know to be impossible. So you do need to slice into two pieces, and that's where this sort of native large gate restriction comes from. All right, so with that, we're going to look at an example, sort of just see how it all fits together. We have here a Z-type weight-2 stabilizer, and then we've broken down on the right into ion trap gates. So I've made two sort of choices here. S prime is the primed values are for the second stabilizer here, or second C-naught. And basically I've chosen S and S prime to be opposite signs, so that the first control knot is rotating in the positive direction, and the second one is rotating in the negative direction. So this is basically where the slicing is coming into the picture. And then I've also chosen the V's to be the same, and this cancels out the most single qubit gates possible in this particular circuit, where basically there were two X rotations on this line that were both of sign minus V prime S prime and VS. So by having those two directed opposite, we can ignore them. So this is basically what we would claim is the most error resilient weight 2 Z-type stabilizer that you can write down for this particular error model, because stochastic errors are minimized due to having as few gates as possible, and coherent errors are minimized by having the dominant coherent error terms all be directed opposite. All right, so with this, we're going to sort of start looking at sort of some results. We look at two codes, the 913 rotated surface code and the 913 Bacon Shore code. So the surface code is looked at in these papers by Tomita and Svore, along with Baum and Delgado. Bacon Shore has been looked at by Dave Bacon, of course, Alafaris Cross, and many others as well. And things to notice here are that the surface code is a LDPC code, so it has very small stabilizers. So that means that no matter what distance you're trying to slice to, you can still have only weight 2 and weight 3 body operations in order to implement our technique. However, Bacon Shore is not LDPC. So in theory, a distance 3 would need weight 4 stabilizers, and in general, you would need D+1 body gates, are not stabilizers, in order to slice it properly. What I'm going to show here is a workaround to that sort of large gate technique in order to use the gauges of Bacon Shore to actually slice it properly, or to some level of effectiveness. Okay, so all the results here will be on this testbed circuit. Taken some qubits in 0 state, use perfect encoding, and then apply error correction with gate errors, and then classically measure and decode. The reason we have this perfect encoding is that we're basically trying to look at how do we behave on our subspace. Of course, if your stabilizers are violated, our cancellations will disappear to some extent, and we will talk a little bit about that in a future slide, but we want to really understand we want to not be damaging things that are already good. We're kind of relying on this error correction itself in order to correct unviolated stabilizers and correct other error models. This is just us trying to not have our gate error be the problem. And then all of the data I'll show you, unless otherwise specified, is exactly calculated, and we used Quantum Sim, which is a full density matrix simulator, you can find it here, in order to apply these. Okay, So first we're going to look at a very simplified toy model on the surface code. So I gave myself here wait 2 and wait 3 Clifford operations. So I wrote the circuit out in terms of control not, control ZZ, etc. And then I put errors only on the entangling gates. So my errors were small rotations about the control ZZ axis, etc. So this is a very friendly toy model to our technique, obviously. And so as you can see, it behaves very nicely. So to break down this plot, the x-axis here is this kappa parameter. So kappa equals to 0 is the stochastic end. The sliced and unsliced versions look identical because stochastic error does not see this directional modulation we're making, because the pi and a minus pi rotation are the same, essentially. And then on the coherent end, you can sort of see that if you don't use our technique, common sort of intuition does apply. You see significantly higher error rates at the purely coherent end. However, if you do use our technique at the purely coherent end, we have 0 error because we gave ourselves a clean code state and all of our gate errors are canceling out fully. And then you can sort of see there's these little curvatures here, and that's because our sort of technique has this sort of interesting interaction between the stochastic and the coherent parts of our error model, where as errors build up, they cause cancellations to disappear, and there's sort of, it's not exactly linear. There's some sort of building up where the more error you cancel out, the more errors you can cancel out further down the line. But this is a very simple toy model. It's not exactly a physical system, so we're going to try to look at how to do this in a near-term computer. And with that, we're going to need to understand the gauges in Bacon-Shor. So Bacon-Shor is a subsystem code, which means it has less than the full n minus k stabilizers it could, given its parameters. And that means there are extra free degrees of freedom in your system. And these manifest in terms of these gauge operators. So on the left, we have the stabilizers of Bacon-Shor, and on the right, we have the gauges. So the gauge are these wait 2 x-type operators on the horizontal and z-types on the vertical. And these gauge operators commute with all of your stabilizers. So when you prepare into a state of Bacon-Shor, you can also choose the eigenvalues of 6 of your 12 gauges. And that essentially corresponds to being in Shor's code almost. So what our sort of workaround is to start out in a defined gauge of Bacon-Shor, and then act as if those gauge operators are stabilizers. And I'll show you how that works, or the downsides of that, in a future slide. But the essential idea is that these gauge operators only will have their values flipped as errors and corrections build up. But by just measuring stabilizers, so long as nothing goes wrong, you won't be scrambling these values. However, this does mean that all of our Bacon-Shor results are one-sided. The surface code result I showed you was for x-type logical errors, but the z-types look the exact same. However, in Bacon-Shor, you can only choose to cancel out coherent error on 1/2 of your stabilizer measurements, because you can't be in a simultaneous eigenstate of non-commuting operators, and the gauges themselves do not commute. So you can only be in the x-type gauge, for example. But first, let's look at a one-round example. So this is a Bacon-Shor code where I've taken the circuit and I've decomposed it into those ion trap gates I showed you. So it's all polyrotations and 2-qubit Mulmer-Sorensen gates. And I have put error on all the gates, sort of in that 1 plus epsilon, 1 plus epsilon squared error model that I showed you earlier. As a result, you can see that we have a similar behavior to how we had in the surface code. The difference in sort of the angles is due to the fact that we have more small stabilizers as opposed to the number of stabilizers we had before. But essentially, the same behavior holds. On the stochastic end, nothing is different. On the coherent end, things are very different. But we don't fully eliminate the error in this particular end because there's a single qubit gate right at the end. And if that one goes bad, then you are still screwed. But in general, this does look very similar to how it did before. However, this one is one-sided. But then, when you look at these gauges, what can happen is the gauges can flip over time. So as you have z-type stabilizer measurements, you'll have z-type errors occur. That'll flip an x gauge, and then the correction could feasibly flip another x gauge. So any error can flip up to 2 x-type gauges. So as you apply multiple rounds, you will start to lose your cancellations. And we show this in this plot here. So on the x-axis here, we have the number of rounds. So we had basically that circuit from before, and instead of applying 1 round of error correction, we applied n. And that means that as the second and third round show up, errors have popped in from the first few rounds, and now we're starting to see how does our system perform when we have actual errors being applied already. How do you have, when you have non-perfect code state, how does your stuff look? And then what I have here on this plot are this black line, which is your perfect gauge. So that's everything plus 1, everything as you know it. And then you have this error model here, or this error rate here. The red case is the worst case gauge, which in the distance 3 Bacon-Shor code is 4 of your 6 gauges violated, because if you had all 6 of them violated, your stabilizer would also be flipped. So in this worst case, you would follow this much higher error rate. And that's because you've lost 4 of your 6 cancellations. So this is the one sampled plot, by the way, so you can see there's a bit of jitter on these data points. But we start in the best case because we know what we're sort of putting ourselves into. And then over time, we start to lose our cancellations. And this leads to this sort of higher slope that sort of approaches a somewhere midpoint-ish, some sort of like, average case amongst these gauges. And that's basically what we would expect is what would happen if you don't try to do anything clever. However, this black line is within reach. There's a few different ways you could try to approach it. You could implement Shor's code instead of Bacon-Shor's code, and then you would have your gauges defined as stabilizers, and on one side you could have weight 2 stabilizers. You could slice them. Another thing you can do is sort of apply your stabilizers in like an XZ-ZX alternating sort of cycle. And then if you measure gauge by gauge, so you measure the weight 2 stabilizers or gauges directly and correct only off of the classical product, you would then have a situation where on the second consecutive measurement of a given type, you would know what your gauge eigenvalues were. So if you knew that 3 of your gauges were violated, or 2 of your gauges were violated, you could then have those particular gauges be applied through a circuit that instead of having a plus and a minus rotation, had 2 plus rotations, where the minus sign would then come from the actual value of the gauge itself, and that would lead to a cancellation as well. So as long as you know the state of your gauge or stabilizers, you can still correct. So this does work with poly tracking and stuff of that nature, but or polyframes. But yeah, so there are ways to track this black line. They're more work, and this is sort of the simple, sort of stupid, don't do anything clever kind of way of doing it. But you can still see that we do see a significant improvement over this red line here. And even if you don't apply slicing at all and you keep everything in the same direction, you're actually worse than this red line because all 6 of your gauges hurt you in some cases. But yeah. And then lastly, we have another sort of more physical error model. Here we have fully optimized and canceled circuits. What I mean by that is I've actually taken all the single cube gates and pulled them out of the circuit. In the previous example, I didn't do that because slicing and unsliced circuits have slightly different single cube gate counts, and the sliced ones happen to have better cancellations as well, so it seems sort of like an unfair comparison. But here, these are the best circuits we have for this following error model. And I've also added in Z-type Stark shift errors. So these are errors that do not interact with our technique. They just make things worse, and they're sort of make things more realistic and have some unsliceable error involved. And what you can see is that under this particular error model, the Bacon-Shor plot does still lower as before, but surface levels off. And that's because in the surface code, when you slice with only weight 2 gates, because this is all near-term current ion trap stuff, you can't slice the middle 4 stabilizers. You can only slice the stabilizer on the boundary of the surface code. And it turns out that just for this particular error rate and error model, surface code essentially just levels off. It just doesn't care how coherent your error is. Things don't get better, but they also don't get much worse. And then in the Bacon-Shor case, as we see, we do still see an improvement, but it doesn't end up getting as low as it does before because of these Z-type errors. Note this is a log plot, but we are still seeing relatively significant, almost order of magnitude improvements. So with that, I want to talk about the last sort of thing I have to say, which is how we can get around this rotational issue. So dynamic decoupling is a technique we've talked about a few times, and basically corresponds to, let's say, in a very simple case, if you have some sort of constant Z-type rotation according to your qubit, you can apply X-type gates in even time steps and essentially flip half of your Z-type errors. They'll cancel out. You can think about our technique as sort of dynamic decoupling on gate error. So we break our stabilizer into 2 pieces that look the same, so they add up. And then if you apply them in the same direction, because you, for example, don't have control of that S parameter, that rotational direction, then if you conjugate by some Y operator, assuming this is an X or Z-type stabilizer, and this is a bit of an abusive notation, but this Y, I mean a single qubit Y on just any of these n lines, not necessarily all n of them, this would then basically flip the direction of this gate sort of without you having to control it yourself. So you can think of dynamic decoupling as sort of not having control of your error, normal slicing as if you had a switch that could change the direction of your dephasing, you would obviously just flip the switch every other time step. And if you don't have access to that switch, you can just do regular dynamic decoupling again. However, because you can only slice into 2 pieces, you don't have much of design space, so you can't do a lot of the more interesting dynamic decoupling sequences that exist out there. And then this does give you results that are almost identical to the ones we have, except that because you have extra gate count, you have extra errors from that, and if your single qubit gates aren't very good, you'll lose much of your cancellations. And then other studies of this sort of dynamic decoupling, quantum error correction overlap can be found in Eng, Lidar, and Preskel, along with a recent paper by Zhenyu Kai, Xiaosi Xue, and then Simon Benjamin, and I think Zhenyu is talking later to me tomorrow. And then, yeah, so with that, I want to quickly conclude. Our technique significantly reduces the impact of these over-rotation type errors on our system. There's no overhead in the way of actual qubits, gates, or timing, as long as you have access to these particular gates we ask for. And then you can apply it to a wide variety of codes. We preferably ones that have small stabilizers or have a lot of symmetry and built in from the subsystem sort of structure in order for you to have not huge requirements on gates. With that, here's the citations. Here's my email in case you have any questions. And then I'd like to thank the collaborators, the host of the conference, and you guys for listening. All right.
Thanks very much, Dipto, for the nice talk. Other questions?
Thank you. Very good talk. So, question is there a way to use this in a fault-tolerant fashion, so that, because what you described, the measurement would be generalizing this sort of naive, non-fault-tolerant measurement, and that propagates and multiplies errors.
Oh, you mean like because it's direct measurement? Yeah. Sort of like from off of one ancilla?
Yes.
So this is kind of based on, actually, I think I have the citation here. But in this paper, we talk about direct measurement of stabilizers and how these certain codes fall under a class of things called compass codes, which has a poster over there, I believe, where direct measurement is actually fault tolerant. And then even under this structure, it remains fault tolerant. So a gate error on your ancilla propagates up and still looks like, basically, you'll always have errors that are perpendicular to your logical error direction. So ancilla failures do not cause you to have a distance drop. But that's separate work. It's just that it does happen to still hold even when you apply it through our technique.
Any more questions over there?
I have a question to the comparison between the surface code and the Bacon-Shaw. So here, is it correct that you do this slicing technique for both cases?
Yeah, so we slice both cases. However, because surface code has weight 4 stabilizers, and these circuits are all in terms of weight 2 things, the boundary stabilizers for weight 2 do look exactly like that example I showed you, where you can slice them perfectly. However, the bulk ones, we still alternate the signs, and that helps you to like third order or something. There's some cancellations that occur, but the main cancellations do not occur because they're not in the same direction.
Okay. But should I then understand it correctly that if you didn't do this slicing, the surface code would still be a flat line here?
If we didn't do that, the surface code actually get worse because we do still have cancellations on the boundary.
I see.
So if you don't slice, this does look, it goes up a little bit. We didn't put all 4 of the pictures because it just became really a busy plot.
Okay.
But yeah.
Okay, thank you.
Mm-hmm.
Any more?
Hi, so when you had the comparison to dynamical decoupling, you were saying if you pad it with Y gates, that's one way to kind of flip the direction of SR. But earlier on, you seem to be implying that you think that in the ion trap, there's a way to just perform the controlled SL and the controlled SR such that you go in the opposite direction. And if you over-rotate, then you over-rotate by the same manner as you would. But is that really how the Molmer-Sorensen gate works? I mean, are there 2 Molmer-Sorensen gates?
It corresponds to I don't want to say anything wrong and get called out by an experimentalist, but I'm pretty sure the phase of the Raman beams that you apply on your Molmer-Sorensen gate is the detuning. Okay. Yeah, so I think it's like a pi over 2 and a 3 pi over 2, or a 3 pi over 2 and a pi over 2. And depending on which choice you make, you get.
So either like detune above or detune below or something?
Yeah.
Okay.
But yeah, so in ion traps, we do have this degree of freedom. If you don't in your architecture, then you could still do it this way.
Okay. One more question.
There's one in the back, I think.
So the numerics were done on the quantum sim simulator. Mm-hmm. If I understand correctly, the quantum sim was originally designed for the transmit processor. So have you already done some simulations based on your techniques for transmit using available gates from transmit processors?
I have not. I wrote my own little addition to quantum sim for ion trap stuff, and I just used those. So I haven't looked at ion trap at superconducting error models yet, but you can put in T2 times and then see how they would interact as well. We just haven't done it in this particular work.
let's thank Dripto again.